All right, good morning, everyone, again. Today, we are going to continue chapter 9, hypothesis testing, and we are going to hopefully finish chapter 9 today. And in the last 4 weeks, starting Tuesday next week, we are going to start chapter 10, then 11, then we are going to go back and chapter 5 and 6. We are going to finish the semester with those two chapters. So last time we have started hypothesis testing on Tuesday, and we have said that hypothesis, the null hypothesis H0 and the alternative hypothesis are two mutually exclusive statements. The null hypothesis is usually to indicate the normal case, and if our sample provides sufficient evidence against that normal, or depending on what you're testing against. So the alternative hypothesis is accepted in favor of, or the null hypothesis is rejected in favor of the alternative hypothesis if our sample shows significant difference from that null hypothesis, null distribution. So in general, we are going to be doing very similar things as we did in confidence intervals. We are going to collect sample. We will be testing our hypotheses in this chapter are going to be about means, differences between means, proportions. So we are going to estimate the population mean. We are going to compute the sample mean. If the standard deviation of the population is given to us, we are going to compute the standard error in our sample mean. And if not, we are going to again estimate that. If we have a large sample, we will be using the sample standard deviation to estimate the standard error. And this test statistic that is shown in the second step of the general method for testing hypotheses, the test statistic will be the standardized form. Standard, for example, it will be standardized normal distribution for that normal value for that sample mean. So it's very, we didn't standardize it actually. We were finding first, we had a confidence level or alpha, which we will call this level of significance of a test. That alpha was used in confidence intervals first to find a z, a standard z value, then unstandardize that z by translating it with our sample mean and extending the margin of our confidence interval with that z value times the standard error. So we're not going to find that z from alpha directly. Here what we're going to do is alpha is going to define our self-acceptance rejectance regions, and we are going to standardize this test statistic will be the standardized version of our mean of the sample with respect to a certain hypothesis. So we are going to some additional thing here. In confidence interval, we don't hypothesize about, for example, what if the population mean is this, okay? Whether the sample is significantly different than that population mean. The midterm exam, we already had the midterm exam. You mean the final exam? There will be no second midterm. So the midterm exam was, like a couple of weeks ago. So there will be no second midterm exam. So you may, hopefully you did not miss the first midterm. Okay, so that's good. So there won't be a second midterm exam. There will be one midterm and one final exam. So we won't have another midterm exam. And final exam, I think it's like, it's also announced final exam dates. I think it's in July, 3rd of July or something. I have that in my calendar actually. June, July. Yeah, this is June. When is the exam? So yeah, the final exam Yeah, it's 8th of July. Okay, so yeah, it's 8th of July. So it's 8th of July, 1:30 p.m. in the afternoon. So yeah, so it's at the start of the second week of July, we're going to have our final exam. So, and we're not going to have a second midterm. We are going to compute this test statistic will be the R Z value computed with respect to that sample data. Okay, so we are going to see what it means. And when you see the examples, I mean, the test statistic that we will be computing here, in Z-test, we are going to compute the Z value for that sample. And we are just going to see Z-tests and T-tests in this chapter. T-test will only be conducted when you have a normal distribution, but your sample size is small. Okay, you know that they're normal, sample size is small, and the standard deviation of the population is not given to you. That's when we conduct t-test. Otherwise, we will be conducting z-test when we have large samples. We will conduct z-test with respect to population means, population differences between two population means, and proportions, and maybe difference between proportions. And if the statistic falls in the rejection region, which we will state this rejection region with respect to the significance level we want to conduct this test, if we are just going to see where this Z test statistic falls in. If it's in the acceptance region, which means like if it's a 0.05 level of significance, means that 95% of the just lands on our Z value is inside the null distribution, where it's 95% of the null distribution is, then we are going to accept the null hypothesis and reject the alternative hypothesis. This does not mean that these are true or false for certain. So with that significance level, we accept to make certain errors. This is what we had where we stopped last time. So the level of significance, for example, if the alpha we have using confidence intervals is called the significance level, and it's also the probability to observe type 1 errors. So we will never, since it's a sample, there is always going to be a certain chance of making an error. So the probability for example, if you decrease alpha, if your significance level is 0.001, okay, 1 in 1,000, for example, it means that you want to limit your probability to observe type 1 errors a lot. You don't want to tolerate any such type 1 errors, which means false positives. Type 1 errors occur when so when the significance level is, for example, 0.001, let me write it here. If alpha is equal to 0.001, which means that the null distribution, the acceptance region, and if we are conducting a 2-level z-test, for example, what it means is that we want the acceptance region as large as possible. So 99.999, all right, is going to be here, and this part is going to be 0.001 divided by 2, 0.001 divided by 2. So this is the probability to make a type 1 error, because that percent, actually this is not 999, actually it should be, yeah, this is percentage, so these two shouldn't be there, right? So 99.9%. This is, I thought this is not percentage, this is ratio, which means that's so this ratio means 0.1% if you convert this to percent. Okay, so this is the probability, 0.001 probability, 1 in 1,000. 1 in 1,000 means 0.1 in 100. Okay, so it should be 99.9. So 99.9 of the area of your null hypothesis distribution here, this is your acceptance region. So what we are going to do is we are going to collect a sample, compute its z statistic for this sample, and we are going to see if this z that we compute is going to fall somewhere on this line. If it is inside this interval, we are going to accept null hypothesis. We'll say that this sample does not show significant evidence against the null hypothesis. So it may be considered as one of those normal cases. But if it falls in this region, we are going to reject null hypothesis in favor of the alternative hypothesis, which may indicate, for example, some extreme case, a person being sick or not. Okay, so significance level alpha directly correspond to the probability of observing type 1 errors, which was so the positive here does not, it depends on what you call positive actually. So let me first try to answer Aral Yekta's question. The positive in this case does not indicate we don't say normal is equal to positive, okay? We don't say this. Normal, null distribution. Here, the positive here is, for example, when you're sick, okay? For example, you got the disease. So having the disease, have disease is the thing that is positive, all right? So here, type 1 error is false positive because you call it, for example, you get some error. So here, let's see the type. If you look at the type 1 error, we reject null hypothesis. We call that person sick, okay? Rejecting null hypothesis is, for example, if you have a z statistic and it falls in here, okay? So you call that you're sick to that person. But if the null hypothesis is true, which means that that person is actually not sick, okay? So normal people, for example, 0.1% of normal people who fall in this normal distribution may still show this extreme cases. This is what you expect. And therefore, when you say you are sick and that person is actually not sick, it means that you have called that person positive. You have the disease, but if that person does not actually has the disease, that's a false positive. Okay, so the type 1 error here is when H1 is true, means that the normal case is true. Not sick is the normal case. Okay, here and we don't say that here. What you may think that positive is being normal is not positive. Okay, being normal is defined as negative in this case, and therefore if you reject H0, you have a positive verdict as the result of the test. Oh, this guy is rejecting H0 is you're not normal. You have the disease. But if that person does not actually have the disease, H1 is true, mean that that person actually is normal, doesn't have the disease. So we make an error, type 1 error. So that this is therefore what our decision, the result of the test, which we made positive, was something wrong. So that's why it's called false positive. Okay, so is that clear? So type 1 errors are called false positives. This is, you can also take a look at this. There's a nice discussion on these things on type 1 errors, specificity, sensitivity, false positive, but it really depends on what you're calling positive. But most of the time when we're conducting a test, we are looking for something extreme, and that extreme is called, so this on Wikipedia, there's a nice article on type 1 errors. So the error rate, usually when we are conducting a test, we don't have these two distributions. So when we're going to conduct a hypothesis test, you're just going to be considering the null distribution. Okay, but you may imagine in machine learning, for example, we also we may have the distribution. For example, if for people who have the disease, they may actually show a distribution that is like this, but we don't know that in our hypothesis test. We don't know this distribution for that alternative. We don't have it. When we are conducting a hypothesis test, we only have the null distribution and we're testing against it. So you may also take a look at this, what we call true, positive, false, negative. There's also specificity, sensitivity. These are also there. So this article may make it easy digest what these errors are. But I usually, as I said, it really depends on what you're calling positive. If you say positive is being normal, then the meaning immediately changes. So first, at the problem, what you call positive should be clearly defined. But this is in most general way, this is how they are defined when we call the extremity, the abnormality as something that our tests results in positive. So again, actually, this is also when you conduct a diagnostic test, when you go into a hospital, they also say the same thing. Even if your test result is positive, it means that you have the disease. Okay. And which is something rare in population to have the disease, right? So false negative, sometimes called the probability to avoid false negatives, is sometimes called the power of the test. And the false negatives type 2 errors will occur when you say you're normal. Okay, you tell that person your test is negative, your test turned out to be here, and you're normal. But if that person is actually sick, has the disease, it means that that's a false negative, and that's will be your type 2 error. And significance level alpha, when we conduct an alpha level hypothesis test, it directly corresponds to our probability of type 1 error. We try to minimize type 2 errors as well, but as I said last time, these two things are competitive. I mean, they are in conflict with each other. You may make, if you want to increase the power of your test, you may get your alpha level. For example, if this person really was sick, in order to have your test to not miss this sick person, you may increase your alpha level to actually decreasing alpha. It means that increasing alpha is meaning that you're going to the significance level here. I mean, your confidence is going to be decreasing in the test. You may reduce the acceptance region. You may increase the rejection region here, saying that I don't want to miss this person. If you don't want to miss this person, if you want to increase the power of this test, you do it at the cost of more false positives, right? If your threshold comes from here to here, it means that the probability to get type 1 errors this time increases. So as I said, these are two measures that are in conflict with each other, but we usually, the most widely used, a good test, for example, the type 1 errors, the accepted type 1 errors are usually 0.05 probability. So 95% confidence is one of the most commonly used cases. Yeah, and when we see examples, these are all going to be more clear. But yeah, this is alpha level test. Alpha will be given to you in the question. You're going to say, let's conduct a hypothesis test with alpha is equal to 0.05 or 0.01. These will be, again, most widely used alphas are going to be the 0.05, 0.01. Those will be the most widely used. And it means this alpha is the probability to reject H0. It's this area that you put around here that you accept to make these errors. So this is clearly an error. When H0 is true and we reject H0, we are making a mistake here. That alpha is that probability that you accept beforehand. If you don't accept that, meaning that if you want to have alpha is equal to 0, since that normal distribution goes all the way to the infinity, it means that you have your confidence interval from minus infinity to plus infinity. So you're always accepting H0. So which means that you have a test which says everyone, you don't have the disease, you don't have the disease. So if you tell everyone you don't have the disease, is it possible to make any false positives? No, because test is always negative. But what is the power of such a test? 0. You will be missing all the real people with the disease. So when when you make alpha 0, the power of the test will also be 0, or the probability to make the error false negative rate will be 100%. You will be, everything you say will be false negative to sick people. Okay, so this is power is sometimes called sensitivity, sometimes called recall, or true positive rate. The probability to find the abnormal case when that case is there. Okay, when that case is really the case where when there is really abnormality, what is your probability to catch that case, the probability to catch a disease? So that's the power of the test, and it's not directly, this probability is not directly given by our hypothesis test parameters alpha, because we don't know this distribution most of the time. Okay, so in the hypothesis test, we will not be using the alternative hypothesis distribution. But in later, when you take machine learning courses, you may see that we may take a look at this distribution as well and try to find some, make some decisions based on the distribution of the alternative hypothesis as well. So here's a link to sensitivity and specificity on Wikipedia if you want to learn more about these things. And depending on what we're looking for in our test, for example, if we are looking for an extremity in which the certain thing is higher, for example, if it's a test for a disease where you're looking for certain levels of some blood measurement, if it's too high, then that's something bad. Then your test will be a right tail z-test like this, where you will be looking for the abnormality will be the excessive amount of that measurement in the blood, that particle in the blood. Okay, if it's too low, for example, if that person has 0 of that measurement, that may be no problem. Okay, if you're what we're looking for, whether it's going to be a right tail z-test or left tail z-test, whether it's a two-sided t-test, really depends on the semantics of what we are testing here. What we will call extreme, what we will be calling, if we are going to call this person has the disease, if that measurement is very high, then it's a right tail t-test. If it's very low, then that's a problem, then it's going to be a left tail z-test. The right tail and left tail z-test are the different thing than what we do in confidence interval. We are not giving an interval, bounded interval, when we conduct these two tests. And the area under the curve entirely, the whole area under the curve to the left-hand side or to the right-hand side will be our alpha. But here, if you're having a two-sided z-test in which maybe we're looking for cases where both extremities are bad, and in that case, we will conduct a two-sided z-test where this area under the curve to the left is alpha over 2, and to the right it's also alpha over 2. The null distribution is the distribution which, when we have for the assumption that the hypothesis, null hypothesis, is true. And it's always, the null hypothesis is always an equality. And as I said, the reason that it's always an equality is to have a specific distribution like this. For example, the connection rate is 8 megabits per second. Okay, so or 80 megabits per second. That's a specific equality, and based on that, and assuming that it's normally distributed, we get ourselves the null distribution based on that. So it's always an equality, and it will have a fixed specific distribution assuming that null distribution, uh, the null hypothesis is correct. Okay, so we are going to again see examples of that. Most of the time, in our z-test and t-test, the null distribution will not be skewed like this. They will be symmetric. It will be the standard normal table, or the student's standard normal distribution, or the student's t distribution with a certain degree of freedom. Okay, but this is just the figure on the book is just showing a generic distribution, which shows that your null distribution could be an exponential distribution or a gamma distribution with some skewness in it. Now, the most common test, we are going to just look at z-test and t-test. Z-test, as I said, we're always going to conduct z-test when we have large samples. Even if we know the standard deviation of the population or not, if we have a large sample, it will be a z-test. We will just refer to the t-test when we have a small sample and the population standard deviation is not known. Okay, so when the population standard deviation or population variance is not known, we are going to use t-test only for that, and only when the sample size is small. Okay, if the null distribution of the test statistic is the standard normal is called z-test. Here are population mean proportion differences, the same thing we did in confidence interval. Here's how we conduct a two-tailed z-test. We collect data from some normal distribution with unknown mu and known sigma. If we know the sigma of the population, if it's given to us, we are going to set our test, maybe null hypothesis, maybe mu is equal to some given value. So this mu0 is some given value to you, versus the alternative hypothesis in the two-tailed test, our mean is actually not equal to that. So we first find this z alpha over 2 that defines our acceptance rejectance region. So this looks like a confidence interval, but it's in the standard normal table. So z alpha over 2, this is the case where we have, here is 0, this is z alpha over 2, and z alpha over 2. Okay, so we form this at the standard. This is not like a confidence interval in the non-standardized form that we conducted earlier. Now, what we do is we standardize our sample mean, and then we call this the z-score, or the z-value, the test statistic v, since it's a z-test. So as you can see, what we do here is not so much different. This is the same formula. This is just assuming that we're just standardizing x bar. If you know what is this sigma divided by square root of n, is our standard error. It's the standard deviation of x bar. So you just, since x bar is normally distributed asymptotically, it's normal, and it's again unbiased, therefore the expected value of x bar is mu0, under the assumption that if the null hypothesis is true. So that's something different than confidence interval. So this mu0 here is the given thing in the question. If the null hypothesis were true, this is how you would standardize it. So if maybe you're going to reject the null hypothesis, the actual mean of this sample may not be mu0, but under the assumption that null hypothesis is true, the entire test is conducted based on that. So as you can see, this is just making x bar standard normal. It standardizes this and checks where it falls in this interval. If it falls in this interval, we accept null hypothesis. If it's outside this interval, it means that this x bar is something extreme. Okay, it's not. It's in those rejections regions which cover only alpha over 2 percent. It's not percent, alpha over 2 times 100% of the entire population. Okay, so that's and when we conduct a one-tail t-test, we just make this interval. The acceptance region is either from -infinity to z alpha, or from -infinity to minus z alpha over z alpha, or from plus infinity to z alpha. So depending on whether we are conducting so what I'm saying is this. So this is where z alpha is. The acceptance region will be from minus infinity to z alpha if we are forming a right tail test. If it's a left tail test, the acceptance regions will be from plus infinity to minus z alpha. Yeah. So while we're standardizing here, so why did we use mu 0? Because we don't know mu. Mu is not given. So mu here is just the variable name that we don't know. Okay, mu 0 is given to us, that it's in our test. Mu 0 is given to us. For example, the connection speed is 8 megabits per second. That 8 is what we use here. Okay, mu is not known, and here mu 0 is the value that is given in the question. And we standard, again, this is really important. We standardize it assuming null distribution is true. Okay, so this is the test is conducted against a null distribution, against H0. So therefore, that's why we use the H0's mean, which is mu 0. And so yeah, so the alternative is not known. For example, mu A is not known. We don't know that. The test is always against some null distribution. That's our normal case. We're testing against it. If the sample has evidence, for example, if the sample is really coming from a different distribution, the z-value here is going to be either very large or very small, right? I mean, because if this mu 0, if this x bar is coming from a different distribution other than mu 0, then this z-value is going to be either really something negative or something positive, which means that it's some extreme case. And when we're comparing it against this population, we will see that, oh, it's not part of this population, it's some extreme sample, and we're going to then reject H0 and accept the alternative hypothesis. That's why we're using mu 0. And when we're conducting a one-tailed test, here H0 will never be, the null hypothesis can never be greater than or equal to something. We cannot have, for example, in a one-tail test, mu is greater than this. How are you going to, when I say, for example, mu is greater than 3, and if I tell you draw the distribution of H0, what distribution is it going to be? For example, can you draw a normal at mu is equal to 4? Or is it going to be, is this the null distribution? Or is this the null distribution? There will be infinitely many null distributions if you write your null distribution like this. You will not be able to have a specific distribution. That's why the null distribution has to always be an equality. Even if we are conducting a one-tail test, in the normal case, we're going to say this mu is equal to u, even if it's a one-tail test. And one-tail means that we're looking for an extreme case at one end of this null distribution. It's either on this end or on this end. So we are going to form our acceptance and rejection regions based on what kind of an extreme we are looking for. Okay, so null distribution has always be an equality, and the main reason is that, as I said, if you say null distribution, if it's greater than, if this is your null distribution, mu is greater than 3, the null distribution will be a collection of infinitely many distributions, and you cannot test against a specific distribution. That makes it not possible. That's why it has to be an equality. All right. And yeah, when we conduct, for example, one-sided right-tail z-test, here the only difference is that, as I said, the z statistics is exactly the same. So this is even if it's a one-sided test, H0 is still an equality. Now we're testing, we're looking for cases where it's greater than. So we're looking for extremities where our z statistics is large. So therefore, any small value of z is not an unnormal case for us when the alternative is looking for uh, large values of our sample. So when the alternative is significantly larger than this, okay, the mean actually is larger than this mu zero. Uh, if we're looking, our alternative is like this becomes a right tail test, then the entire region to the left hand side from minus z infinity to z alpha is our acceptance regions. We are going to accept it as normal. Only if our z value here that we compute from the sample is, if x bar is significantly larger than mu zero, this is going to give us a very large z value, like 5, 6, 8 standard deviations larger than mu zero. So in standard normal distribution, what is the probability that a value is going to be 8 standard deviations larger than the mean? It's a very small probability, right? Therefore, probably this is not this x bar, this sample is not probably coming from h0. Therefore, I'm going to reject h0 in favor of h, the alternative hypothesis. So this is what we will be doing. And similarly, one-sided left-tailed z-test is just the reverse of this, or acceptance. Now we will be looking for z values that are extremely small, negative, because if x bar, if you're looking for a left-sided test, x bar is going to be probably smaller than mu zero, and z value here is going to be some negative number. So if it's very negative, -7, -8, it will probably be in the rejection region, and we are going to reject null hypothesis in favor of the alternative one. Now, by the way, last year, these times we also, the pandemic had started last year, and I was also conducting these video recordings. It wasn't like a synchronous lecture like this, but I have some sessions that I solve some exercises at the end of this chapter. So I'm going to also put that on YouTube. So I'm going to, so some exercise solving session. There's a video of that I did last year, and I'm going to share it with you again this year. So you will, I think it will make all these chapter 9 more clear if you also watch that exercise solving session video. Okay, so here I want to check the book on this actually. When I at the beginning of this lecture, I told you that we conduct t-test only when we have small sample, right? Now, I mean, from these slides, I understand that even we have large, when we have unknown variance, I understand we always conduct t-test whether the sample size is small or large. This is actually a little bit in conflict with what we did in confidence interval. So I'm going to verify that, whether even if we have large samples, do we still conduct a t-test if we don't know the standard deviation or the variance of the population? Okay, I think when we have a large sample, the t-test, this n-1 degrees of freedom, for example, if you have a sample size of 1,000, when n is 1,000, you'll see that if you conduct a t-test with 999 degrees of freedom, it will probably be the same as z-test d-value, right? So if the book just says that whenever you have unknown variance, you always use t-test, I mean, there is no conflict here, actually. You may still conduct t-test if your degrees of freedom is too large, 999. Let's go to the end of the book to see. So this is 291. So if you go to the T table at the end of the book, where is it? Right here, A5. So this is the T table. After 200, if you look at these values, even if after a sample size of 200, they will be exactly when it's, for example, after 200, these values that you see here, they will be exactly the same as the z values you get from the normal table. So you may as well be conducting z-test. So what we have did And confidence intervals is actually valid. It says unknown variance, you conduct t-test. We conduct t-test when the sample size is small. If you have a sample size 100, 200, you may as well conduct the z-test or t-test. Your result will not be different, whether it's a z-test or t-test when your sample size is large. And we use the sample variance, which is an unbiased estimator for population variance. So this is how we conduct our sample variance from a given sample. And here, this is the z-test. This table from the book describes everything. When we're comparing a null hypothesis of a single population, we may be checking the population mean, population proportion. What we will be doing is we conduct the standard error. So actually the population variance assuming that H0 is true. Okay, and here actually this is not the population variance, this is the standard error. It's the variation of our estimator. The variance, as you can see, the variance of our estimator is going to be this, and it's going to be this. This P0 could be is the one that is given to you in the question. Assuming that proportion is correct, you're just going to be using that to compute assume the population variance. And here, the only thing you compute from the sample is either X bar or the proportion. All the other thing on the right-hand side is given to you in the question, okay? And the other z-test that we perform, maybe comparing two population means, comparing two proportions, assuming that there may be a test which says that the difference between these two proportions is at least D. Okay, so testing whether the difference between proportions is given this given value. Or this is the last test here is the same as saying D is 0. This hypothesis is saying that these two proportions are equal to each other, or they're not different from each other. We may be testing that one as well. So if our test is that they're equal to each other, we conduct actually the population, the pooled variation by assuming a single p-hat. Here that this p-hat is computed here as a pooled variance where the pooled proportion where the entire, if the null hypothesis is saying that they're equal, then combine all these two samples together, which will give you m plus m data points, and just compute the ratio for the whole set. This ratio for the whole set is going to be your estimated proportion for that sample, this pooled proportion, assuming that the null hypothesis is true, of course, and this will be your standard error. And this will be all of these values you compute on the right-hand side, they will be standard z values. Okay, and t-test is very similar to this table. Here, sample size is n, unknown standard deviation. Testing, again, a single population mean, testing the difference between two population means, and the difference between two population means is something. And here, if there are two cases where we assume the standard deviations of the two populations are same, our degree of freedom will be this. If we have unequal standard, we assume unequal standard deviations. This is not assuming that the means are different. We already assume that means are different. As you can see, the null hypothesis say that the difference between the means is equal to D. So we are not making any assumption on the equivalence of the means, but these are the assumptions about standard deviations of the populations. If we assume they are equal, we compute our statistics like this by using the pooled standard deviation of the sample. And if we assume they're not equal, we cannot use the pooled one because we assume they're not equal. So we have to conduct our standard error individually by using the sample standard deviation for each of these samples differently. And the degree of freedom we have here is going to be very difficult. We have seen that complicated formula a week ago about confidence intervals, which is referred to here as 9.12. So here, yeah, the z-test and t-test, everything that you need here, how you're going to standardize your variables, what you're going to compute from that is given here. I can actually, yeah, there are actually some test examples here. Before we have our first break, before I continue with this slide, let's actually look at an example here. It was 291. Yeah, somewhere around here. Z-test, let's go to Z-test and let's take a look at the first example in the Z-test. Yeah, Z-test for means and proportions. Yeah, let's look at this example 925. Z-test about a population mean. The number of concurrent users for some internet service provider has always averaged 5,000 with a standard deviation of 800. So the standard deviation is given to us. And the mean is given to us as well as 5,000. After an equipment upgrade, the average number of users at 100 randomly selected moments, so we have a sample of size 100. Now its average, the sample average is 5,200. Does it indicate at a 5 level of significance that the mean number of concurrent users has increased? So we are only looking for extreme cases that, I mean, this 5,200, is it something abnormal? Did it really change? Or is it still coming from the assumption that the average is still 5,000? Okay, so we have the significance level is given to us, 5% level of significance. So that's our alpha. Alpha is going to be 0.05. The mean number of did the mean number of concurrent users increase after this upgrade? So this is the hypothesis test that we are going to conduct. And we also make an assumption here that the last sentence is also important. Assume that the standard deviation of the number of concurrent users has not changed. So in other words, this x bar, which is this the x bar, which is 5,200. Those samples that we collected with 100, they have the same standard deviation of 800. Otherwise, we would not be able to compute standard error with this. In order to be able to compute the standard deviation of x bar, this sigma has to be assumed to remain the same as 800, or if this last sentence was not given, we would need to probably compute, instead of the sigma, we would have to compute S, the sample standard deviation from the samples that we have collected. Okay, so this last sentence makes sure that you may use that 800 as when you're computing your standard error. So 800 divided by the square root of 100 will give you the standard error in x bar. And we compute the z. So this is a one-tailed z-test. So alpha is 0.05. We are going to conduct a one-tailed t-test. Our z alpha at 0.05 is 1.645. So what we're going to do is this 1.645 is our threshold for z value, which determines where our acceptance and rejection region is. If we get a z value here, which is larger than 1.6, we will consider it as an extreme case, and we are going to reject the null hypothesis. And indeed, when we do it for the values that are given to us, so the average was 5,200, assuming that the null hypothesis is true, mu was given to us as 5,000. So this 5,200, it's like this z value basically is asking this 5,200, how many standard errors it's larger than 5,000. So this is exactly doing that, right? I mean, if you take the difference, it's 200. Is this 200? How many standard deviations, how many standard errors it is away from this mean of 5,000? and this is the standard error is given. This is 2.5 standard errors away. And this 2.5 is larger than 1.6. So what we do is we reject H0 in favor of the alternative hypothesis, which means that given this evidence that the sample that we collected, the sample that we collect indeed indicates an increase in the average number of concurrent users. So here, that's our step 3. How? Okay, it's larger than 2.5. It's larger than 1.645. What do we say? It belongs in the rejection region. We reject the null hypothesis. So this last sentence here, basically saying that the data we have collected, the sample of size 100, it provided sufficient evidence in favor of the alternative hypothesis that the mean number of users has increased. Okay. If they gave the new standard deviation in the question, and if the new standard deviation was given, that's actually, it would never be directly given. I mean, if the standard deviation of the new cases were given, it would probably mean that we would also know the mean of the new case. And if it's different, then we would not be conducting a statistical test then. So it's really unlikely to know the standard deviation without knowing the mean, right? So therefore, they would not be able to give us the mean of, but maybe it is possible. If the measurement error, for example, is changed, and if it's given to you, then we could use that. We could use that new standard deviation because this standard deviation that is below here that is used to compute the standard error of X bar. So we would be able to use that actually. It's not the one that is corresponding to the null hypothesis. The denominator of this is really the, let me write here, it's really the standard deviation of X bar. So you need to write here the denominator, the standard error here, which is the standard deviation of X bar. If we were able to compute that standard error of X bar by using some other standard deviation that is given to us, we would be able to use that. So the reason we were able to use this 800 was due to the last sentence. If the last sentence says that now the standard deviation after the equipment upgrade, the standard deviation now becomes 600, and we would be using that 600. Okay, so the denominator is always, we should compute this one for the denominator. All right, I hope that's clear. And let's have a break now. I will then conduct more examples and we will finish the remaining part where we are going to talk about p-value and the relationship of this hypothesis testing with the two-tail hypothesis test with the confidence intervals that we have built earlier. So yeah, before the break, there's another question that I want to address. Rejection area means that at the beginning we reject the hypothesis that the users increase. If it's bigger than our z-value, we reject the R rejection. So let me try to understand. The rejection area actually means that the rejection area is the place where we say that's an extreme case, and that extreme case is, for example, 5% of the population. Then I accept that even in the null hypothesis, 5% of the population falls into that extreme area. So means that if you reject it incorrectly, that will be an error, type 1 error, but you accept it in the first place by conducting it as a level 0, the level of significance to have 0.05. So like having alpha is equal to 0.05 means that I just limit my extremities and limit those extreme cases to 5% of the normal null distribution. Okay, and if our z-value indeed falls in that extreme case, then we say, okay, that's I have observed something extreme. So it's like if you're going to convict a person, setting the significance level is like I have to see this and evidence these evidences to convict you. Okay, so if those evidences are just a small evidence and you still convict the person, it means that you have your significance level is not that low. I mean, your alpha is going to be some large value, which will mean a very large rejection region. So you're going to convict many people. So the rejection area means that when we have a z-value in that rejection region, we reject our null hypothesis. If it's bigger or smaller, if it's a two-tailed test, for example, this was a one-tailed test. Therefore, when we get a z-value larger than that, we do that. But if it's a two-tailed test, either the computed z-value may be too small or too large, then we will reject our null hypothesis. So what you write is true. Yeah. Okay. If it's bigger than our z-value, the z-value is 1.6. The computed z-value larger than this, that means that it's in the rejection region, and that is completely determined by your level of significance. If alpha was 0.1, this will probably be like 1.2 or 0.9. It will be a smaller value for alpha 0.1. Okay, 90% confidence means that you will be rejecting lots of things. Means that you're not confident in your rejections. Your confidence decreases. But if you want to be more confident, you make your alpha to be equal to 0.0001, for example. If alpha is 0.0001, that z-value is going to be really large, like maybe 4.5. Only if you observe a very extreme case, then you will reject it. So having a smaller alpha is like you need more evidence to reject the null hypothesis, to accept in favor of the alternative one. If this alpha becomes 0.1, 0.2, having alpha 0.2 means that 20% of the population is considered extreme, and even a small evidence will make your z-value, will make your sample in that extreme case, and you will be labeling it as abnormal, okay? Which means that you have 20% of your normal population is actually will be by mistake labeled as abnormal. So I have more and more examples, and at the end of the chapter there are a lot of examples. I think all these will be much more clear. I will continue with example 9.26 after our 10-minute break. So I will stop recording now, and we will